In the last video, I made the point that there's more to evolution by natural selection than genetic change alone. Sometimes, the selective pressure is very definitely to maintain the status quo, to leave things exactly as they are. But that's not always the case. Sometimes selective pressures lead to adaptation and even the evolution of entirely new species. There are various forms of selective pressure, changes in circumstance and environment that favour adaptation. In this video, we'll look a little more closely at what those changes might be like. They tend to fall into various groups, or types of selective pressure that we can identify and describe. Stabilizing selection is the most common type of selection pressure. In fact, it's so common that it's taken for granted, and most people, although aware of it, don't think of it as natural selection at all. But that's exactly what it is. This is the form of natural selection that keeps things exactly as they are, exactly as they've always been, so far as anyone can remember. This is survival of the fittest at its most prevalent and least obvious. Stabilizing selection is what ensures that the majority of garden birds, sparrows for example, can fly. Any sparrow that can't fly is likely to be eaten by domestic cats long before it can produce offspring to duplicate its flightlessness. So the status quo, flying birds, is maintained because flight is an adaptive trait for birds in UK gardens. The fact that flight may not be so adaptive in other settings is irrelevant in this context. It's vital to the survival of garden birds in Britain. The same is true of children born without vital organs. They die. This means that they're selected out of the gene pool, and so only those children who are essentially similar to their parents survive. This stabilizing selection keeps the genotype, in this case the human genetic makeup, stable. Returning to wings, it's easy to see why birds might evolve flight if it helped them to escape predation. But what would be the evolutionary advantage of losing flight? Why might some birds become flightless? The fact is that every evolutionary adaptation has both a payoff and a cost. Big, strong wings might help a bird to escape predators, but they're also expensive in terms of energy and nutritional value to build and maintain. In a world full of cats, that expense is worth paying. But an island population with no natural predators, well, birds might be better off expending all that precious energy in other ways, developing strong beaks or fast-running legs, for example. After all, if there's nobody on the ground to escape from, and nowhere to fly to that you couldn't walk just as easily, who needs flight? Directional selection is a type of selection that occurs when selection pressures favour organisms at a particular end of the distribution curve. For example, in a population of humans, some, those with the darkest skins, will be good at blocking out harmful radiation from the sun, and others will be less efficient. In our species' African birthplace, black skin prevents skin cancer, a disease notorious for affecting white-skinned Europeans like myself in hot countries such as Australia, where the lifetime skin cancer rate amongst Caucasians is almost 50%. As the population migrated north out of Africa, the climate became cooler and the sunlight less intense. At this point, natural selection favoured those humans who were less good at blocking out the sun and better at making use of sunlight and vitamin D. So natural selection favoured those individuals whose skins were lightest, even though they're not really all that pale, but they were slightly better at processing sunlight in northerly climes. Throughout the generations, the selection pressure remained, and in each generation, those with the least dark skin are favoured until eventually the least dark skin becomes the most pale skin, and over long periods of time the whole population in the northern hemisphere changed to have white skin because that's good for processing vitamin C and vitamin D. In each generation, the population moves a little further in the direction of pale skin. This is directional pressure. Disruptive pressure is different. Although any form of pressure can lead to speciation, disruptive selection may be the easiest to make sense of. This is because it takes a single species and effectively splits it down the middle. Imagine, for example, a population of herbivores, four-legged grass eaters that live in herds on wide open grasslands. Some of these animals will be tall, slim and long-legged, the fastest runners. Others will be smaller, with shorter legs. They may not be very fast runners, but they will be able to hide more easily in the tall grasses of the savannas. These are the two extremes. Then there will be the individuals in the middle of the distribution curve. These individuals won't be so good at hiding as their smaller counterparts, and they won't be as fast running as their long-legged fellows. They will be much easier for predators to catch and kill. So natural selection will favour two distinct ends of the population, the short and slow and the tall and fast. It's not difficult to see how animals in both these extremes would grow either progressively shorter and less conspicuous or progressively taller and faster, until over time we end up with two separate species, the tall and the short, with no middle ground, fairly tall and fairly fast. Those middling individuals have been eaten and died out. Disruptive selection, by favouring two extremes, can take a single species and select individuals with different traits until two completely new species emerge where once there was only one. Sexual selection takes almost no thought to understand. In most species, including humans, females generally are choosy about who to mate with, and males generally are not. This is almost certainly to do with the amount of parental investment each sex needs to make in the business of growing and raising young. But that's not the issue here. All we need to understand is that males usually compete for the favours of females, and female choices usually determine which males pass on their genetic material, have kids, and which do not. Therefore, sexual selection plays a major role in selecting for attractiveness, a quality we'll pick up on later in this series. Kin selection. Sometimes it's difficult to pass on your own genes, but it is possible to pass on genes by proxy. This means that the more closely related you are to someone else, the more likely they are to pass on your genes, or at least a nearly identical copy of your genes. This is why people tend to help their relatives advance, and why parents are so often willing to sacrifice themselves for their offspring. The power of kin selection should not be underestimated. In terms of evolutionary psychology, it leads to a variety of behaviours such as altruism that would be difficult to understand from an evolutionary perspective without this concept of kin selection. It's through these various selective pressures that different genes become dominant. Ultimately, this is how speciation occurs. Our series on evolutionary psychology will refer to all of these at different times to try to explain why people tend to behave the way that they do, and in some cases, suggest ways for us to improve upon the situation.
I'm Stuart Sorensen, and this is Mind the Care training. If you found this video useful or helpful in any way, please feel free to share it around and click the like button. Oh yes, and while you're at it, if you click on the little character icon that's on your screen right now, you can subscribe to the channel and you won't miss any other videos. Thank you for watching.